Exercise 2.10. Prove theorem 2.5. Let X be a topological space, A be a subset of X, and Y be an element of X. Then Y is in the closure of A if and only if every open set containing Y intersects A. Alright, well, this is not particularly interesting in the case where Y is in A itself, because, well, A is a subset of its closure, so then Y is certainly in the closure. And an open set containing Y, well, it intersects A at the element Y, right, if Y is in A itself. So this is really an interesting statement only when Y is not an element of A, as in this picture here. Then it's saying that Y is in the closure if and only if Y is so close to the set A that if you take any neighborhood of Y, it's going to overlap A in at least one point. All right. That's the intuition behind this statement. Now to prove it, you notice it's an if and only if statement, so we have to prove two directions. So let's begin with the forward direction. For that, we will assume that Y is in the closure of the set A. And we got to prove that every open set containing Y intersects A. So let U be an open set containing Y. And I'm going to do proof by contradiction. So suppose that it contains Y, but it does not intersect A. Okay? It does not intersect the set A. All right, well, U is an open set. We know something about a closure, which has to do with closed sets. So maybe we should look at the complement of U and see what we can find out about that. All right, so then X minus U, well, it's the complement of an open set, so it's a closed set. And, well, as you can see up in the picture here, since U does not intersect A, the complement of U contains A, right? So X minus U is a closed set containing A. And, well, what does that say about the closure of A? Right, the closure is the intersection of all closed sets containing A. So that must be a subset of this particular closed set containing A, right, of X minus U. Okay. Well, what does this say about Y? Right, this implies that Y, which we assumed was an element of closure of A, therefore it has to also be an element of X minus U. Right. That's a contradiction because U is supposed to be an open set containing Y. Right? Y can't both be in U and in its complement. All right, so that finishes the forward direction of the proof. And now for the backward direction, we have another little visual aid here. And okay, so this time we're going to assume that every open set containing the element Y intersects A. And we want to prove that Y is in the closure of A. Okay, so I'm going to do proof by contradiction again. Suppose that Y is not in the closure of A, except I didn't type what I wrote, what I said. Let me try again. Is not in the closure of A. There we go. Well, what does that mean? Okay. Well, if you're not in the closure of A, the closure of A is the intersection of all of the closed sets containing A. Okay. So to not be in there means that there's some closed set B containing A which does not contain Y. Okay. Then there exists some closed set B containing A, but not containing the element Y. All right. Well, what we know has to do with open sets, and B is closed. So we should probably look at the complement of B. All right. So it follows that complement of B is an open set, and well, we said that B does not contain Y, so its complement does, right? Containing Y. Which does not intersect A, right? Because if B contains A, then its complement does not intersect A at all. Okay, but that's a contradiction, right? Because we just found an open set that contains Y and does not intersect A, and it directly contradicts our assumption up here. That takes care of the backwards direction of the proof, and in both directions we have completed the proof of this if and only if statement.